Hello, in this video I will show you how to make an inverter schematic in electric and simulate it with LT-Spice. So first open electric, double click on it. Now we will adjust the windows. So just drag this message window up. Here you will be able to see all your error messages, whatever they appear. So you go to window, adjust position, tile horizontally, then window, message window, tile with edit window. This is electric, this is the workspace, this is the components and the explorer bar. Whatever files we will be creating, we will store them in certain libraries, and within libraries we will create cells which will contain our schematic and layout, which you will learn to make further. So first we will make a new library. So we'll go to file, new library, and since we are making an inverter, let's name it as an inverter and say OK. Now your library is created. Within the library you need to make cells. So we'll go to cell, new cell. Since we are making a schematic, we will select schematic and type INV. Inverter. I'll say OK. So here is your library and here is the schematic cells. Now we'll go to components. These are the components which you will use to make the schematic. This is a PMOS, this is an NMOS, a power node, a ground node. This is a node which you will be defining as input or output. So let's just start. First click on PMOS and don't drag it, just move your cursor and paste it. Then you click on NMOS and just click on the workspace. Now your PMOS and NMOS are in place. Let us take the power. Click, 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 click. Remember, you don't have to drag it. Now we'll be giving one input and checking for the output. So we'll require two nodes. So we'll put one here and the other one will be here. Now you have to align this well. To align it, you can just turn on the grid, Ctrl G, so that it will be better to align, or else other option that you can do is you have to open the object properties, like click on the object, then go to cell, edit, properties, object properties. Here you will see the X position and Y position. Other object properties are width, length, which we will be adjusting now, but first let us just adjust it in a proper way. So the X position is 1.5 and Y is 6. What is this X position and Y position? We'll click on the NMOS, go to edit, properties, object properties. It's minus 1.5 and 2.5. So you can say they are in one line. Similarly, check for others and see if they are in one line. Or else you can just use the grid. Now we'll just zoom it. So we'll go to window and we'll say fill window. Now it's nice and clear. Now let's make the connections. To make the connections you need to draw wires, right? But electric doesn't call wires, it says arcs. And to draw arcs you have to left click on the source and right click at the destination. Left click, right click, and you have a line drawn. This blue thing that you see here is an arc. So just left click, right click, left click, right click, left click, right click, left click, right click. This makes the inverter ready, but it is not completely ready because we haven't yet defined the width, the length, and also we have to name the devices which we have used. So we'll click on PMOS here and we will open edit, properties, object properties. We will make the width 10 and let the length be 2. Similarly, click on NMOS, edit, properties, object properties, width as 10, length as 2. Because these values, as you can see here, width is the larger number, like larger in size, and length is the smaller number. These are defined in the C5 models. Now if you remember the C5 file, you have to link that file with the devices, right? So you need to name the devices. So we click on the device, and to name them we will go to Tools, Simulation Spice, Set Spice Model. This will provide a name to our device. Then we will click on NMOS, we will go to Tools, Simulation Spice, Set Spice Model. But now the naming is such that it says it is a spice model. We need to say what exactly it is. So we will click on the spice model. When you click on the text, an X mark will appear, a red colored X mark, as you can see here. If you are unable to select the text, so just press Ctrl and then click. Because sometimes, as you can see, this thing is placed above the transistor, right? So when you have to select something that is one below the other, you have to press Ctrl and then click. So since I have clicked here, I will again open properties and I will write PMOS and say OK. Now I have defined PMOS. I need to define NMOS too. But first I'll show you how to use a shortcut so that it will be easier for you to do things. Like you can put shortcuts for every possible thing you want. So we'll first click on the particular object, then we will go to File, Preferences. In Preferences, we will go to General. In General, Key Binding. In Key Binding, we will open Edit. In Edit, we will open Edit Properties. In Edit Properties, we will click on Edit Properties. Whatever you have, the shortcuts, first we will remove them. So we will say Remove. Again go there, File, Preferences. You will reset them. After you reset, you say Add. In first stroke, you type P. So whenever you press P, the properties will open. And you say Add, Apply, OK. Now, I'll just click on this and press P. Now this opens my properties. And I'll name it as NMOS. Make sure you write capital NMOS and PMOS and not small letters. Now we need to give input and output. So we will click here. And to name the input and output nodes, we have to export them. So we will go to Export and Create Export. Here we will type in. Click on this. We will type Export, Create Export, and we will say Out. So with this, your inverter is ready. Now we have to see if it works. So for that, we'll write the spice code. To write the spice code, in the components bar, we will go to Miscellaneous, MISC, click on it, and you can see spice code. So click on spice code and just click. Now press P to open properties. Tick on the multi-line text box because you just don't want to write one line, but you have to write few lines of code. Now the code begins such. First we will apply VDD. We need to specify what VDD we are giving. Is it 3 volt, 5 volt, 12 volt? So we will write VDD. That is the name. Then where is the connection? It is from VDD to ground. Now as you might have observed that we did not mention this power node as VDD or this node as ground like we did for in and out. That is because electric just takes the power as VDD and takes the ground as GND, so we need not specify it. So we'll say VDD 0, DC 5, since I want to apply 5 volts. Now we will give the input. So say Vin 0 DC. So this is the format, name of the signal, the node, the in and 0. So I am applying a signal Vin between in and 0. Okay, and it is a DC signal. Now to check for the output, I need to give a pulse which will start from say 0, then rise up to 5 volts, then again stay high, like stay at 5 for some time and then come down. So to apply a pulse, I say PWL, that is piecewise linear model, in which we will first give the time like 10 nanoseconds. At 10 nanoseconds I want a voltage of 0. Then I say at 20 nanoseconds I want 5 volts. Then at 50 nanoseconds I want 5 volt again. At 60 nanoseconds I want a 0. So it is a pulse, as you can see, that I have applied. You can apply any waveform that you want. After you give the input, you need to set the load. So you will say C load space out 0. Out 0 is because you are connecting the load between the terminal out and 0. 0 is the ground. And the value of the capacitor is 250 femtofarads. After you have defined the load, now you will have to measure the rise and the fall times, right? So you will say dot measure, MEASURE, transient analysis. I will say TF, as I want to measure the fall time first. Then I will say trigger V out, as I want to measure the output signal. Then I'll say val VAL is equal to 4.5. Then I'll say fall is equal to 1. Then TD is equal to 8 nanoseconds. Target TARG VOUT. Val is equal to 0.5. Fall is equal to 1. So this is the code to measure the fall time. It says measure the transient analysis. TF is the name, like I can say anything here, any name I can give. So then what I tell the signal is trigger start measuring, that is start to measure the signal V out from a value of 0.5 and know that it is a falling signal. Start all this after a delay of 8 nanoseconds. You have to measure up to the output value, that is target V out, up to a output value of 0.5 and fall 1. Fall 1, that still it is a falling signal. So this will measure the fall time. Similarly, you have to write dot measure for the rise time. Now value will be equal to 0.5 and I will say rise is equal to 1 because it is a rising signal. But I will say the delay is say around 50 nanoseconds. Just because my fall time comes after, my rise time comes after 50 nanoseconds. Then target V out value is 4.5 and rise is equal to 1, as it is a rising pulse. After you mention all this, you will say tran for transient analysis, and you will write 0 to say 100 nanoseconds. After that, you will write dot include. Now this dot include will help you to include the C5 models file, and that we have linked with the PMOS, right? Like we define this PMOS here and NMOS here. This just means that we have specified that whatever is written for PMOS in the text files is applicable to this device here. Whatever is written for NMOS, like whatever the voltage thresholds, so we will say dot include the C5 models, that is, and where is that C5 models text file stored? In the C drive, in the folder electric which we made. So we will say C. I am just specifying the directory. Electric C5 models are text, and we will say OK. Now with this we are done with writing the code. So we are done writing the spice code. We'll just do window, fill window. Now what does this function fill window does? Fill window will paste all your designs, all your schematics in this workspace. Like whatever you have done in the workspace, it will just fit it to the screen. Okay, to zoom in, you can just zoom in or zoom out. Now we will just simulate this. To simulate, we will go to Tools, Simulation Spice, Write Spice Deck. So this is your LT Spice. When you scroll down here, you will see your Spice code. Now we will see the waveform. So for that, we will click on the waveform, and we will click on V in. Then we will press Ctrl and click on V out. That is to select multiple signals, and say OK. So this is the input, the blue color signal, and red is the output. Now you want to see the rise and fall time, right? So we will go to View, Spice Log Error, Spice Error Log. Here you can see that the fall time is 3.29 and the rise time is 3.76 nano. Now after this, you will have to go to Tools, Control Panel, Netlist Operations. You have to go to Operations and check that automatically delete dot raw files is marked as no, and say OK. Then you can close this. Now there is another window which pops up. In this window also you can see your signals. You can just click on this trans signals, double click on in, double click on out. So you have in and out. Now this makes your schematic ready. But now suppose if you want to use the same schematic for say some larger circuits, so we will make an icon view. To make an icon view, we will click on View, Make Icon View. You will see fill window. You will see that a box has appeared on the right hand side of the screen. So just go to Explorer and you will check in inverter. You have one more cell created saying inverter icon. Click on it, go to that cell now. But this is not the shape of an inverter, right? So you will just change the shape to the shape of an inverter. So for that, first we will bring this out terminal. Just draw a box and bring it on the other side. You can pull it right away, but then sometimes the wire gets extended like this, which we don't want. So just draw a box and pull it out. Then click on this box and press delete. Now go to components. You will be able to see that the components have changed from what was there earlier. These are the components that you have for icon. Those were the components for schematic. And for layout, you will definitely have different components. So click on the triangle here, paste it here. Now you want to rotate it. So we will go to edit, rotate 90 degrees, right? Now you want a circle in front of this triangle, right? So just click on the circle and put it here. Again, no dragging, just click there and click here. But the circle is too large, so we will just change the size. So click P, which will open the properties. Say the X size is 1 and Y size is 1, and OK. And adjust it. If you are somehow not able to adjust the circle, then again open properties and make sure that the unit, that is the X position and Y position, is in 0.5 times. It is not 0.25 or 0.75, because here the grid is adjusted to the smallest, which says that you can move within the grid by 0.5 places. You can't move it by anything more or less, right? So just say if it is 0.75, it will still move by 0.5 and it might not be aligned. Now adjust the out terminal. Then click on this node here and drag it. This time you have to drag the node. No clicking will do. And this is the icon of your inverter, which is ready to be used. You can go to inverter schematic and check. Okay. Now what we'll do is we'll create, say, another cell. And we will simulate the icon instead of the schematic. So to name this, I'll say inverter underscore sim. Keep it as schematic and say OK. Now what will I do here? I will click on this inverter icon and I will drag it. After dragging, I'll just leave the mouse so that it is pasted. Now I want to simulate only this icon. Now this icon will have the same properties as this inverter. So I will copy this code. So this is the code that I have just pasted. But now this V in and out, in and out is the input and output signal, of course, but then that belonged to this particular schematic. We had these exports, right? Here this in and out is of the icon. We don't have any in signal or out signal for our schematic here. So I will just draw two arcs, left click, right click, left click, right click. And instead of exporting, I'll name the arcs. Double click on the arc and I will say it is in. Double click and I will say it is out. So now I have specified where I want to give my in signal and where I want my out signal. And I will just run them. Right spice check. Now it says previously found tran analysis. Now that means that somewhere else your code is still present. So just delete the earlier code. And run. Look, it's working. I will check the output. Yes. File. Spice error log. It is still the same. So this completes your inverter schematic. Now you can just shut this window down, but before that we will just save it. Inverter glib, save.